What if I told you that everything you can see in the night sky, every star, every galaxy, every distant point of light, represents less than 5% of what actually exists? And what if the telescope that just proved this is currently staring into a darkness so profound that it's rewriting our understanding of reality itself? The James Webb Space Telescope isn't just taking pretty pictures, it's shattering assumptions scientists held for decades. Galaxies that shouldn't exist are appearing in places they shouldn't be. Black holes are growing at impossible speeds, and the universe itself? It's not just bigger than we thought. It's so incomprehensibly vast that what we can observe might be nothing more than a cosmic grain of sand on an infinite beach. If that doesn't terrify you, it should. Because what Webb is revealing isn't just about distant galaxies, it's about the fundamental limits of what humans can ever know. And today, we're going to walk through exactly what this telescope has discovered, and why those discoveries are forcing scientists to question everything. But before we dive in, I want to know, where in the world are you watching this from right now? Drop a comment below with your location and what time it is for you. I absolutely love seeing where my viewers are from, and it's amazing to think that while you're reading this, someone else might be watching from the complete opposite side of the planet. Alright, let's get into it. Here's something most people don't truly grasp about space. When you look up at the night sky, you're not just looking across distance, you're looking backward through time. This isn't poetic language, it's literal physics. Light moves fast, incredibly fast. It travels at roughly 300,000 kilometers per second, making it the absolute speed limit of the universe. Nothing can move faster. Yet despite this blistering pace, the universe is so absurdly large that even light takes time to cross it. And that time delay fundamentally changes what we see. Think about it this way. When you glance at something across the room, you're seeing it as it was a few nanoseconds ago. The light had to travel from that object to your eyes, and even though the delay is microscopic, it exists. When you look at a building down the street, you're seeing it microseconds in the past, still too small to matter in daily life. But now scale that up. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The sun? 8 minutes in the past. If our star suddenly blinked out of existence right this second, we wouldn't know for another 8 minutes. We'd continue basking in sunlight that was already travelling through space when the sun ceased to exist. And from there, the delays explode beyond anything our human brains evolved to comprehend. The nearest star system, Alpha Centauri, appears to us as it was over 4 years ago. The centre of our own Milky Way galaxy shows up in our telescopes 26,000 years late. And when we observe Andromeda, our neighbouring galaxy, we're witnessing light that departed its stars 2.5 million years ago, long before humans existed, before our ancestors even walked upright. Every single point of light in the night sky is a timestamp, a frozen moment from cosmic history. The farther away something is, the further back in time we're actually seeing it, which means when astronomers point their telescopes at distant objects, they're not just studying far away places, they're excavating the past. But here's where it gets stranger. The universe isn't static, it's expanding. And not just expanding like objects flying apart through space, the space itself is stretching. Imagine dots on the surface of a balloon. As you inflate it, the dots move farther apart, not because they're sliding across the surface, but because the surface itself is growing. That's what's happening to space, and when space stretches, it stretches the light travelling through it. The wavelengths get longer, visible blue light shifts toward red. Red light shifts into infrared. Infrared shifts even further into wavelengths our eyes can't detect at all. This phenomenon is called redshift, and it's critical for understanding what Webb is doing. Because redshift doesn't just change the colour of light, it acts as a measurement tool. The more stretched the light is, the longer it's been travelling, and the earlier in the universe's history it was emitted, redshift lets. Astronomers use light itself as a clock, allowing them to peer back toward the very beginning of time. For decades, telescopes like Hubble focused on visible light. the narrow sliver of the spectrum our eyes evolved to see, and Hubble revolutionized astronomy. It showed us nebulae in stunning detail, captured the birth and death of stars, and revealed galaxies in their full glory. But as astronomers tried to look further back, deeper into the past, they hit a wall. Not because distant galaxies didn't exist, but because by the time their light reached Earth, it had been stretched so far that it no longer fell within the visible spectrum. Those ancient galaxies became invisible to telescopes designed for human vision. Entire epochs of cosmic history were hidden, not by distance alone, but by wavelength. The early universe wasn't dark, it was unreadable. That's why the James Webb Space Telescope was designed completely differently. Webb doesn't look at visible light, it sees infrared. Its massive mirror, spanning 6.5 meters and coated with ultra-thin gold optimized for infrared reflection, collects wavelengths that earlier telescopes couldn't detect. It operates nearly 1 million miles from Earth, far beyond the Moon, at a gravitational balance point where it can remain stable and undisturbed. But here's the critical part. Webb has to be cold. Extremely cold. Because infrared light is closely associated with heat, and if the telescope itself were warm, it would glow in the exact wavelengths it's trying to observe. It would be like trying to study stars while standing inside a spotlight. The signal would be drowned out by noise. So Webb carries a massive sun shield, roughly the size of a tennis court, that blocks heat from the sun, Earth and Moon. On its shaded side, Webb cools down to temperatures colder than you can imagine, around minus 230 degrees Celsius. Only then does it become quiet enough to detect photons that have been travelling for over 13 billion years. When Webb points at a patch of sky that looks completely empty to the human eye, it's not searching for nothing, it's waiting. Waiting for ancient light that left distant galaxies when the universe was still in its infancy. Photons that have been stretched almost to the edge of detection by billions of years of cosmic expansion. And those photons arrive slowly, sometimes one at a time. Webb might stare at the same region of sky for hours, even days, patiently collecting light that crossed nearly the entire observable universe to reach us. The patience required is staggering. But so are the results. Because what Webb finds when it looks into that darkness isn't emptiness, it's history. Galaxies already forming, stars already igniting, structures already assembling. The early universe doesn't look tentative or primitive, it looks active, crowded, busy. There's something profound about this process. Every image Webb captures is a time capsule. Every photon in the frame departed. Its source billions of years ago, long before Earth formed, long before the Sun existed, long before our Milky Way took its current shape. Human civilization, all of recorded history, all of language and culture and technology unfolded while that light was already in transit. By the time Webb detects it, we're not witnessing events happening now. We're witnessing moments that occurred once, impossibly long ago, preserved only in the light still reaching us. Those moments can't be revisited, they can't be updated. They're fossils, frozen in photons. This is why astronomers say Webb doesn't simply observe distant space, it observes deep time. Distance and time are inseparable. Nearby objects reveal the universe closer to the present. Distant objects reveal earlier and earlier chapters of cosmic history, layered behind one another like pages in an ancient book. But even Webb's extraordinary vision has limits. No telescope, no matter how advanced, can see beyond a fundamental boundary, set by physics itself. That boundary is determined by how far light has been able to travel since the universe began. It's called the observable universe, and it's not an edge of space, it's an edge of information. Beyond that boundary, space continues, galaxies continue, stars are born and die, black holes collide, entire cosmic dramas play out forever beyond our reach, not because of technological limitations, but because the structure of space-time itself prevents their light from ever reaching us. Webb hasn't revealed the edge of everything. it's revealed how much exists beyond what we can ever see, and as it pushes closer to that boundary, detecting galaxies brighter, earlier, and more numerous than anyone expected, a deeper realization begins to settle in. If the universe is already this rich at the limits of our vision, then the true scale of everything that exists must be unimaginably larger than anything we once dared to believe. For most of modern cosmology's history, scientists had a clear picture of how the early universe should have looked. It was supposed to be restrained, not empty, but quiet, sparse, a universe still finding its footing. The logic made sense. After the Big Bang, space expanded rapidly and temperatures plummeted. Matter spread out almost uniformly in every direction, leaving behind only tiny ripples, small variations in density that gravity could work with over time. But gravity, while powerful, isn't fast. It's patient. According to the Standard Model, gas needed millions of years to cool down enough to collapse. Dark matter halos needed time to grow massive enough to trap ordinary matter. Stars required extensive periods to ignite and mature. And galaxies, they were supposed to start small, dim, fragile systems that would take hundreds of millions of years to grow into anything substantial. This wasn't guesswork. It was grounded in physics, in the known behavior of gravity, and matter in computer simulations that had been refined over decades. The early universe should have been a construction site, foundations being laid, structures barely beginning to take shape. So when Webb turned its mirrors toward the cosmic past, astronomers expected to find exactly that. A handful of primitive galaxies scattered through mostly empty darkness. Small systems, faint and struggling, barely clinging to existence. A universe in its infancy, tentative and incomplete. Instead, Webb found crowds. Bright galaxies appeared again and again in eras that should have been nearly barren. And these weren't dim flickers on the edge of detection. They were substantial, already structured, already forming stars at ferocious rates. Some contained hundreds of millions of stars, others contained billions. The shock wasn't finding one unusual object, it was finding so many of them. Everywhere Webb looked, there they were, galaxies that according to every model shouldn't exist yet. The universe was supposed to be empty at these distances. Instead, it was buzzing with activity. Within the first 500 million years of the universe's existence, a blink in cosmic time, Webb detected galaxies producing staggering amounts of light. Some contained stellar masses equivalent to billions of suns. Assembling that much matter should have required far more time than the universe had available. Because gravity has rules, it can't be rushed. Gas doesn't collapse instantly. It needs to radiate energy, to cool, to lose the heat that keeps it buoyant. Dark matter halos have to grow through gradual processes, mergers and accretion that take time. Stars must form, burn through their nuclear fuel, and eventually die, seeding space with heavier elements before the next generation can begin. Each of these steps imposes a timescale. You can't skip ahead. It's like trying to build a skyscraper before you've poured the foundation. The process has to unfold in sequence, and yet the galaxies were already there, fully formed, actively making stars, operating as if they'd had billions of years to develop, not a few 100 million. What made this even more unsettling was their chemical composition. Webb detected signatures of heavy elements, carbon, oxygen, nitrogen, in some of these incredibly young galaxies. But those elements don't come from the Big Bang. The Big Bang only produced hydrogen, helium, and trace amounts of lithium. Everything else has to be forged inside stars, and stars only release those elements when they die, when they explode as supernovae or shed their outer layers as they age, which means something unavoidable. At least one earlier generation of stars must have already formed, lived out their entire life cycles and died, all within the universe's first few 100 million years. The cosmic timeline was being compressed. Events that should have taken 1 billion years were happening in half that time, or less. Think of it this way. Imagine expecting to visit a newborn and finding a teenager instead. Not just older than anticipated, but impossibly developed. That's what Webb found. A universe that had aged too quickly. This phenomenon became known among astronomers as the too much too soon problem. When researchers calculated how much total light galaxies should produce in the universe's first billion years, their predictions fell drastically short. Webb's observations exceeded those predictions by factors of 2, 5, sometimes more. That's not a minor discrepancy. That's a red flag. Scientists did what they always do when observations clash with theory. They questioned everything. Was Webb calibrated correctly? Were dust clouds making galaxies appear brighter than they really were? Could gravitational lensing be magnifying distant objects and inflating our estimates? Were assumptions about stellar populations off? They checked and rechecked and checked again. The conclusion held. The early universe was not dim, it was luminous. Some of the galaxies Webb detected were so massive that researchers began calling them universe breakers, objects whose very existence seemed to violate cosmology itself. Because according to standard models, galaxies of that size should not exist at such early times. Period. At first, there was hope that the masses were overestimated. Perhaps active supermassive black holes at the centres of these galaxies were contributing extra light, making the systems appear more massive than they actually were. When researchers factored that in, the most extreme cases did drop somewhat, but only somewhat. Even after accounting for black holes, the early universe still contained roughly twice as many massive galaxies as theory predicted. The problem eased. It didn't vanish. Webb kept finding them, in different regions of the sky, using different instruments, observing at different wavelengths. Every time, the same pattern emerged. The early universe was not sparse. It was crowded. Star formation wasn't struggling to get started. It was efficient, relentless. This forced a fundamental reconsideration. How efficiently does the universe convert gas into stars? In the modern universe, star formation is surprisingly wasteful. Most of the gas inside a galaxy never becomes stars. It's heated by radiation, stirred by turbulence, blown away by stellar winds, or disrupted by supernova shockwaves. Only a small fraction actually collapses into new suns, but early galaxies may have operated differently. For one, the universe was smaller and denser. Matter was packed more tightly together. Gas clouds collided more frequently. That compression could trigger star formation faster and more efficiently than we see today. Another factor, composition. The first generations of stars formed from nearly pure hydrogen and helium. Without heavier elements to complicate the cooling process, gas might have collapsed more readily. Mergers likely played a role too, in the crowded earlies. Universe galaxies were closer together. Collisions were common. When galaxies merge, gas is driven inward and compressed to extreme densities, sparking intense bursts of star formation. Entire generations of stars can form in a matter of millions of years instead of billions. Each of these ideas explains part of the puzzle. None completely resolves it. The early universe remains more active, more productive, and more organized than our models predicted. And then there are the black holes. At the centers of many of these early galaxies, Webb has detected supermassive black holes, objects weighing millions, sometimes billions of times the mass of the Sun. And they're already in place when the universe is less than 500 million years old. This shouldn't be possible. Black holes form when massive stars collapse, but stellar black holes are small, only tens of solar masses. To grow into supermassive black holes, they need to consume matter over long periods, and that growth has limits. As matter spirals inward, it heats up and releases enormous amounts of energy, creating radiation pressure that pushes surrounding gas away. This creates a natural speed limit on how fast black holes can grow, yet Webb keeps finding them, fully grown, already massive, already active. This has forced astronomers to consider scenarios once thought extreme. Maybe some black holes didn't form from stars. Maybe they collapsed directly from massive gas clouds in the early universe, creating seed black holes thousands of times more massive than stellar ones. Or maybe the first stars were far more massive than anything we see today, creating larger black holes from the start. Or maybe black holes grew through rapid mergers, colliding and combining in the dense environment of the early universe faster than anyone thought possible. None of these ideas has been confirmed. None can be ruled out yet, but the implications ripple outward. Because these early galaxies, and the black holes they contain, didn't just exist in isolation, they shaped everything that came after. Their radiation transformed the chemistry of space. Their supernovae scattered heavy elements across vast distances. Their gravity carved the large-scale structure we see today. If they formed earlier and faster than expected, then the entire timeline of cosmic evolution shifts. The universe didn't build itself gradually, it surged. And as Webb continues peering deeper into time, that pattern becomes harder to ignore. The cosmos didn't wait. It didn't take its time assembling the pieces. It moved with urgency, building stars, galaxies, and black holes at a pace that still challenges our best equations. The early universe wasn't fragile, it was fierce, and that changes everything. For most of the 20th century, astronomers believed they had arrived at a reasonable answer to one of humanity's biggest questions. How many galaxies exist in the universe? The method seems straightforward. Point a powerful telescope at a tiny patch of apparently empty sky. Count every galaxy you can detect, then scale that number up to represent the entire observable universe. When the Hubble Space Telescope performed its deepest observation, the famous Hubble Ultra Deep Field, the result was breathtaking. In a region of sky no larger than a grain of sand held at arm's length, Hubble detected nearly 10,000 galaxies. The image felt overwhelming. From it, astronomers estimated the universe contained a few 100 billion galaxies. That number was almost incomprehensible on its own, and for years it stood as the best answer science could provide. Then the James Webb Space Telescope looked at the same darkness. Where Hubble saw gaps between galaxies, Webb found more galaxies. Where black space once separated distant smudges, Webb detected faint infrared glows, layers upon layers of galaxies stacked behind one another, hidden not just by distance, but by wavelength. This wasn't a failure of earlier telescopes, it was a limitation baked into their design. As the universe expands, light from distant galaxies gets stretched into longer and longer wavelengths. By the time it reaches Earth, much of that light has shifted out of the visible range and into infrared. Hubble simply wasn't built to detect it. The galaxies were always there. Their light had just drifted beyond what Hubble could see. Webb was specifically designed to follow that light. In one of its most ambitious projects, Webb focused on a region of sky only slightly larger than 3 full moons placed side by side. For hundreds of hours, it collected thousands of individual exposures, patiently gathering faint infrared signals that had been travelling for over 13 billion years. When those images were combined, the result was staggering. Nearly 800,000 distinct galaxies filled the frame. Let that sink in. 800,000 galaxies in a patch of sky most people would describe as completely empty. To appreciate the scale, imagine printing the Hubble Ultra Deep Field on a single sheet of paper. To display Webb's image at the same level of detail, you'd need a print more than 13 feet tall and 13 feet wide. A wall-sized portrait of cosmic history. And every single point of light in that image isn't a star, it's a galaxy. Each one contains millions, billions, sometimes trillions of stars. Many host planetary systems, many are filled with dust and heavy elements created by countless generations of stellar life and death. The universe isn't sparsely populated with isolated islands drifting through darkness. It's densely packed with structure. But Webb didn't just count galaxies, it measured them. For each one, astronomers determined its distance, mass, star formation rate, and approximate age. This allowed scientists to reconstruct how galaxies evolved across nearly the entire history of the universe. And when they analysed that data, a deeper pattern emerged. galaxies aren't scattered randomly. They cluster, they align, they trace invisible pathways across enormous distances. On the largest scales, the universe resembles a vast cosmic web, long filaments of matter stretching tens and hundreds of millions of light years, intersecting at dense nodes where galaxy clusters form, separated by vast voids where almost nothing exists. This structure had been predicted decades ago by computer simulations. Webb revealed it with unprecedented clarity. Many of the galaxies Webb detected were hidden behind thick dust that blocks visible light but allows infrared to pass through. Entire populations of dusty, star-forming galaxies suddenly came into view, filling gaps where earlier surveys saw nothing, completing patterns that once appeared broken. This matters because the distribution of galaxies isn't just scenery, it's a record, a fossil imprint of the universe's earliest moments. After the Big Bang, matter was spread almost uniformly through space, with only tiny variations in density. Regions that were slightly denser exerted slightly stronger gravity. Over time, matter flowed toward those denser regions, amplifying the differences. Gravity carved space into filaments and nodes, draining matter from surrounding areas and leaving enormous voids behind. It's similar to how water flows over terrain. Rain falls relatively evenly, but over time, water collects in valleys, carves rivers, and leaves high ground dry. A structured landscape emerges naturally. The universe evolved the same way, except the flowing substance was matter itself. Webb's observations show this process began remarkably early. Filaments tens of millions of light years long already existed when the universe was only a few billion years old. Some structures were so large and so organized that they challenged assumptions about how quickly matter could arrange itself. One striking example is a structure astronomers have named the Cosmic Vine, a chain of more than 20 tightly packed galaxies stretching over 13 million light years. These galaxies existed when the universe was still quite young, yet the structure rivals formations that are billions of years older. What makes it especially intriguing is that several of its largest galaxies have already stopped forming stars. They've exhausted or lost the gas needed to create new ones. This is unusual so early in cosmic history. The implication is subtle but important. Environment matters. Galaxies in dense regions evolve differently than isolated ones. Interactions and mergers accelerate their life cycles. Growth happens quickly, fuel is consumed rapidly, and this isn't a rare occurrence. Using Webb data, astronomers assembled the deepest catalogue of galaxy groups ever produced, more than 1,600 groups and protoclusters spanning from roughly 12 billion years ago to just a few billion years ago. These groups represent the building blocks of today's massive galaxy clusters. By comparing groups at different cosmic epochs, scientists can watch structure formation unfold over time like a time-lapse. Early groups appear chaotic with intense star formation. Later groups show increasing order, smoother shapes, slower growth as gravity takes full control. This kind of continuous view across billions of years simply wasn't possible before Webb. Yet for all this density and organization, the universe is also defined by profound emptiness. Between the filaments of the cosmic web lie vast voids, regions tens to hundreds of millions of light years across that contain very few galaxies. These voids aren't small gaps. They're among the largest structures in the universe by volume. If you could somehow stand at the center of one and look in any direction, you'd see darkness stretching for tens of millions of light years before encountering the nearest galaxy. Entire regions of space essentially fail to gather matter, simply because gravity pulled that matter elsewhere. Webb's deep field images capture this contrast vividly. Dense clusters of galaxies appear alongside yawning black regions containing almost nothing. The universe is simultaneously crowded and empty, packed and sparse, structured and void. Which brings us back to the numbers. If Webb's deep fields are representative, and observations in different directions suggest they are, then the total number of galaxies in the observable universe may not be hundreds of billions, it may be 2 trillion or more. For every galaxy we once believed existed, there may be many others hidden beyond the limits of earlier surveys. More galaxies mean more stars mean more planets, more chances for worlds capable of hosting life, more possibilities for intelligence, civilization, art and wonder scattered across incomprehensible distances. The universe becomes not just larger in extent, but vastly richer in content and potential. But here's the sobering truth. Even this extraordinary abundance exists only within the observable universe. Beyond the cosmic horizon, space continues, structure continues, galaxies keep forming, evolving, and dying. Black holes keep merging, stars keep igniting and burning out. And if reality is this densely packed within the portion we can see, then the true scale of everything beyond it, forever hidden from view, becomes impossible to even conceptualize. At first glance, the size of the universe seems simple to understand. The Big Bang happened about 13.8 billion years ago. Light travels at a fixed speed, so it feels logical to assume that the most distant objects we can observe should be about 13.8 billion light-years away. That assumption is completely wrong. The observable universe doesn't have a radius of 13.8 billion light-years. It has a radius of about 46.5 billion light-years, giving it a diameter of roughly 93 billion light-years. This isn't speculation, it's a measured result, supported by observations of cosmic expansion and the behavior of ancient light, and it violates what feels like common sense. The reason this seems impossible is that it clashes with how we instinctively think about motion. We know nothing can travel faster than light through space. That rule still holds. No galaxy is racing outward at impossible speeds. No signal is breaking the cosmic speed limit. Instead, the universe grows in a far stranger way. It stretches space itself. When we say distant galaxies are moving away from us, it's tempting to imagine them flying outward like debris from an explosion. That mental picture is deeply misleading. On cosmic scales, galaxies aren't really moving through space at all. They're being carried apart as the space between them expands. A helpful analogy: imagine dots drawn on the surface of an inflating balloon. As the balloon expands, every dot moves farther from every other dot, not because the dots are sliding across the surface, but because the surface itself is stretching. None of the dots occupy a special position. All of them see every other dot moving away. The universe behaves exactly this way. When a distant galaxy emitted the light we're detecting today, it was far closer to us than it is now. Over billions of years, while that light travelled toward Earth, the space between us and that galaxy continuously expanded. By the time the light finally arrived, the galaxy had been carried tens of billions of light-years farther away. This is why we can observe galaxies whose light has been travelling for more than 13 billion years, even though their current distance exceeds 46 billion light-years. Light isn't crossing a fixed distance, it's moving through a distance that grows while it travels. Imagine running on a treadmill that keeps speeding up. Early in the universe's history, expansion was slower, and light made steady progress. As time passed, expansion accelerated, stretching distances faster and faster. Some photons managed to reach us because they started their journey early enough. Others never will. This creates a boundary, not a wall or an edge, but a horizon. The cosmic horizon marks the limit of what can ever be observed from our location. Beyond it, light cannot reach us, not because it runs out of time, but because the space it must cross grows faster than light can traverse it. And here's where things become deeply unsettling. Space doesn't end at the cosmic horizon. We know this because the universe looks essentially the same in every direction we observe. The number of galaxies doesn't thin toward an edge. The cosmic microwave background, the faint afterglow of the Big Bang, appears nearly uniform across the entire sky. That uniformity would be impossible if space abruptly ended just beyond our view, so the universe extends beyond what we can see, but it does so in a way that permanently hides vast regions from us. Beyond 46 billion light-years, galaxies still exist. Stars continue forming and dying, black holes continue merging, planets orbit. Entire cosmic histories unfold in regions that will never influence us and can never be influenced by us. No signal from those regions will ever reach Earth, not because our technology is inadequate, but because space-time itself prevents it. Even more unsettling, this boundary isn't static. As time passes, the observable universe grows because light from more distant regions has had more time to reach us. The horizon slowly creeps outward, but simultaneously cosmic expansion is accelerating, causing space to stretch faster now than it did in the past. These two effects compete. The result is a universe where some objects briefly become observable, only to later slip beyond reach forever. Galaxies we can see today aren't guaranteed to remain visible. Their light continues stretching, shifting into longer wavelengths, becoming progressively fainter and more diluted. From our perspective, those galaxies appear frozen at a particular moment in their history. They fade gradually, and eventually they disappear. This isn't a distant abstraction. It follows directly from measured expansion rates. If the universe continues behaving as it does now, then in roughly 100 billion years, every galaxy outside our local gravitationally bound group will cross the cosmic horizon. Future observers would see a universe containing only a small cluster of nearby galaxies, surrounded by darkness. They might never know that trillions of other galaxies ever existed. They'd have no evidence of the cosmic web, no way to detect the expansion of space, no ability to understand the Big Bang. Their cosmology would be fundamentally limited by timing, by when they happen to exist. This changes what observation even means. The observable universe isn't the universe, it's the portion that happens to be observable from where we stand at this moment in cosmic time. Move to another galaxy, and the observable universe changes. Different regions enter view, others disappear beyond the horizon. Every location in space defines its own observable bubble. This leads to strange situations. Two galaxies can both be visible from Earth yet unable to see each other because they lie on opposite sides of our horizon. Light from both reaches us, but light from one can never reach the other. From their perspectives, Earth itself may lie beyond their cosmic horizon. There's no privileged vantage point, no centre, no place from which the entire universe can be seen. Every observer sits at the centre of their own observable sphere, forever cut off from vast regions of reality. This is why pushing deeper into space matters so profoundly. By detecting galaxies closer to the cosmic horizon than ever before, we're forced to confront the limits of what knowledge itself can reach. Those distant galaxies are no longer where their light began. Their continued evolution, their mergers, their ultimate fate, all unknowable to us because that information is still travelling through space, stretched by expansion, and in many cases will simply never arrive. What we see is not what is, it's what was. And even that view is fundamentally incomplete. Beyond the observable horizon lies the unobservable universe, regions that may contain galaxies, clusters, and structures just as rich and complex as those we can see. Some cosmological models suggest the universe may be infinite. Others suggest it's finite but unimaginably vast. Either way, the observable universe is almost certainly only a fraction, perhaps a tiny fraction, of the whole. James Webb hasn't revealed the edge of the universe. It's revealed that there is no accessible edge. Space continues indefinitely beyond what we can ever observe, forever hidden by the finite speed of light and the accelerating expansion of space itself. And as this realization settles in, another question becomes unavoidable. If expansion hides so much of reality, then what's driving that expansion to accelerate in the first place? To answer that, we have to confront the most dominant and most mysterious component of the cosmos. For most of the 20th century, the story of the universe felt stable and predictable. The Big Bang set everything in motion, space expanded outward, and gravity went to work, slowly trying to pull that expansion back together. The great cosmological debate wasn't about whether gravity mattered, it was about how the story would end. Would the universe expand forever, gradually slowing down, or would gravity eventually halt the expansion and pull everything back together in a big crunch? Every version of that debate shared the same fundamental assumption. Gravity was in control. That assumption didn't survive the 1990s. Astronomers were studying distant stellar explosions called Type Ia supernovae. These explosions are remarkably consistent. They shine with nearly identical brightness each time they occur, making them reliable cosmic measuring sticks. The method is elegant. Measure how bright a supernova appears, compare that to how bright it should be, and the difference reveals its distance. Combine that distance with how fast the host galaxy is receding, and you can reconstruct the expansion history of the universe. What those measurements revealed was shocking. The universe wasn't slowing down, it was speeding up. Distant galaxies were farther away than they should have been if gravity were gradually easing the expansion. The farther astronomers looked, the clearer the pattern became. Expansion hadn't merely continued, it had been accelerating for billions of years. Something was pushing space apart. To account for this behaviour, cosmology was forced to introduce a new ingredient: dark energy. Dark energy doesn't shine, it doesn't absorb light, it doesn't clump into stars, planets, or galaxies. We don't observe it directly, we infer its existence solely from its effect on space itself, and that effect dominates everything. Current measurements indicate that dark energy makes up roughly 68% of the total energy content of the universe. Ordinary matter, everything familiar to us, accounts for less than 5%. Dark matter makes up most of the rest. The visible universe we see and study is a small minority of what actually exists. What makes dark energy especially bizarre is how it behaves as the universe expands. Normal matter thins out as space grows. Double the volume of space and the density of matter drops by half. Radiation dilutes even faster. Dark energy doesn't follow this rule. Its density remains constant even as the universe expands. As space grows larger, the total amount of dark energy increases. This creates a runaway feedback loop. More space produces more dark energy. More dark energy drives faster expansion. Faster expansion creates more space, and the cycle continues. Over billions of years, this quiet loop shifted the balance of cosmic power. Early on, matter dominated, allowing gravity to sculpt galaxies, clusters, and the cosmic web. But as expansion diluted matter, dark energy steadily took over. About 5 billion years ago, dark energy became the dominant influence on cosmic expansion. Since then, it's been in full control. The James Webb Space Telescope doesn't detect dark energy directly, but its fingerprints are visible in everything Webb observes. The extreme stretching of ancient light, the immense size of the observable universe, the way distant galaxies recede and gradually fade, all of it shaped by dark energy. Without dark energy, the universe would be far smaller. The cosmic horizon would sit much closer to us, and vast regions of space we can currently observe would have never entered our view. Dark energy expanded our observable window, and simultaneously limited what we'll ever be able to see. Because dark energy doesn't just shape the present, it determines the future. If dark energy remains constant, as current observations suggest, expansion will continue forever. Gravity will still hold galaxy clusters together, but everything beyond them will slowly drift away, crossing the cosmic horizon one by one. Trillions of years from now, observers inside a galaxy like the Milky Way would see a universe containing only nearby stars and little else. Darkness in every direction. No evidence of other galaxies, no cosmic microwave background, no way to deduce that a Big Bang ever occurred. The universe would still exist in its full vastness, but it would appear almost empty to anyone observing from within. However, this picture is complicated by one of the deepest unsolved problems in modern cosmology, a problem James Webb was expected to help resolve. Instead, Webb made it more acute. When astronomers measure how fast the universe is expanding today, they don't get a single consistent answer. They get two different values depending on the method used. One approach studies the cosmic microwave background, the faint afterglow released when the universe was only about 380,000 years old. From subtle patterns in that radiation, scientists infer an expansion rate of about 67 kilometers per second per megaparsec. The other approach looks at nearby objects. Astronomers measure distances to galaxies using Cepheid variable stars and Type Ia supernovae, then compare those distances to how fast the galaxies are receding. This method consistently produces a higher value, around 73 kilometers per second per megaparsec. Both measurements are precise, both have been repeated and refined, both have been scrutinized extensively. They simply don't agree. This discrepancy is known as the Hubble tension, and it represents a serious crack in our understanding of the cosmos. Webb was supposed to resolve it by refining distance measurements to unprecedented accuracy. Instead, Webb confirmed the higher expansion rate measured locally. The tension didn't disappear, it intensified. This leaves cosmology facing uncomfortable possibilities. Either there's an unknown systematic error hiding in one of the measurements, our assumptions about the universe's history are incomplete, or there's new physics we haven't discovered yet. One possibility is that dark energy isn't truly constant, that its strength has changed over cosmic time. Another is that the early universe behaved differently than we assume, imprinting patterns in the expansion that still echo today. Each possibility carries profound consequences. The expansion rate determines the universe's age, its size, and its ultimate fate. If we're misunderstanding it, then many conclusions drawn over decades may require revision. There's also a more extreme scenario that can't yet be ruled out. If dark energy grows stronger over time instead of remaining constant, expansion could eventually overwhelm gravity even on small scales. Galaxy clusters would be pulled apart, galaxies would dissolve, stars would be ripped from their orbits. In the most extreme version, sometimes called the Big Rip, even atoms could be torn apart in the distant future. Current evidence doesn't favour this outcome, but the uncertainty remains. What's already clear is that dark energy dominates the universe. It stretches space, hides vast regions of reality beyond our reach, and determines what future observers will be able to see and what they'll never know existed. It's the reason the observable universe spans 93 billion light-years. It's the reason most of reality will forever remain inaccessible to us. And yet, dark energy alone can't explain the universe we observe. Because while it pulls space apart on the larger scales, something else must hold matter together on smaller ones. Something must allow galaxies to form instead of dissolving into uniform emptiness. That force is also invisible, equally mysterious, and just as essential to everything we see. To understand how the universe builds structure even as it expands, we need to examine the unseen framework that holds it all together. If dark energy governs how the universe expands, then dark matter governs how it assembles itself. Without dark matter, the universe revealed by James Webb simply wouldn't exist in any recognizable form. Galaxies would never have formed, clusters would have dispersed, large-scale structure would never have emerged, the cosmic web would be absent, the universe would be nearly uniform, a thin, cooling fog with no stars, no planets, and no observers. Dark matter doesn't emit light. It doesn't absorb radiation. It doesn't interact with ordinary matter in any way we can directly detect. And yet it outweighs everything we can see by more than 5 to 1. Roughly 85% of all matter in the universe is dark matter. Every star, every galaxy, every glowing nebula exists within a framework dominated by something fundamentally invisible. What we observe isn't the structure itself, it's merely the illuminated surface of a much deeper architecture. The first hints of dark matter appeared nearly a century ago. Astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving far too fast to be held together by the visible matter alone. They should have been flung apart, yet they remained bound, as if embedded in something massive and unseen. Later, astronomer Vera Rubin studied how stars orbit within spiral galaxies. She found that stars in the outer regions were moving at speeds that should have ejected them into intergalactic space if visible matter were all that existed. But they didn't escape. They stayed in orbit, moving as if each galaxy were embedded in an enormous invisible halo of mass. That unseen mass was dark matter. As observations expanded, the evidence multiplied. Entire galaxy clusters showed the same problem on much larger scales. Individual galaxies moving too quickly to be held by the gravity of stars and gas alone. Gravitational lensing revealed further proof. Massive objects bend space-time, distorting the light from background galaxies. Astronomers detected distortions in regions where little visible matter could be seen. The gravity was there. The source was invisible. Again and again, the conclusion became unavoidable. Most of the universe's matter is hidden from view. What makes dark matter so crucial isn't just how much exists, it's how it behaves. Unlike ordinary matter, dark matter doesn't collide with itself or lose energy by emitting radiation. It moves through space almost without friction. Because of this, dark matter began clumping extraordinarily early. Shortly after the Big Bang, the universe was nearly uniform, with only tiny variations in density imprinted during the earliest moments. Dark matter responded first. It quietly gathered into growing concentrations while ordinary matter remained hot and resistant to collapse. These concentrations became massive invisible halos, everywhere, dominant and invisible. As the universe cooled, ordinary matter began falling into these dark matter wells. Gas, collected and compressed under gravity. Temperatures rose, nuclear fusion ignited. The first stars were born. Over time, those stars gathered into galaxies, not randomly, but precisely where dark matter had already shaped the landscape. The visible universe traces an invisible blueprint. This process produced one of the most striking features of reality, the cosmic web. On the largest scales, matter is arranged in vast filaments stretching tens and hundreds of millions of light years. These filaments intersect at dense nodes where galaxy clusters form. Between the filaments lie enormous voids where almost nothing exists. This structure isn't coincidence, it's gravity at work on a cosmic scale. Webb's observations have brought this architecture into sharper focus. By cataloguing hundreds of thousands of galaxies and measuring their distances, astronomers can map how matter is distributed across space and time, revealing patterns once confined to computer simulations. The pattern is unmistakable. Galaxies align along filaments, they cluster at intersections, they avoid vast empty regions, they follow an invisible skeleton that shapes everything we see. Webb's ability to see through dust and detect faint distant galaxies fills in gaps earlier surveys missed. It shows how early these structures emerged, revealing that filaments were already well established when the universe was only a few billion years old. Matter flows along these filaments, not metaphorically, but physically. Gas streams through space like traffic on cosmic highways, feeding galaxies and allowing them to grow. Galaxies don't evolve in isolation. They're connected, supplied, and guided by pathways defined by dark matter itself. Even our own Milky Way participates in this process. Our galaxy drifts through space along routes shaped by invisible mass. Its motion is guided by gravity rather than chance. For decades, the cosmic web existed mainly in simulations, inferred from theory and indirect evidence. Recently that changed. Using gravitational lensing, astronomers detected dark matter directly along the filaments themselves. By measuring subtle distortions in the light of distant background galaxies, they revealed mass where no visible matter could account for it. Dark matter wasn't confined to galaxy clusters alone. It was stretched across space, threading the universe together. This transformed the cosmic web from a theoretical framework into an observed structure. The universe isn't a loose collection of galaxies drifting apart. It's an interconnected network, shaped and sustained by invisible matter. At the densest nodes of this network lie galaxy clusters, the most massive gravitationally bound structures in existence. These clusters act as anchors, pulling matter along filaments toward their centers and reshaping galaxies as they fall inward. Gas is stripped away, star formation slows or stops, galaxy structures are altered. Webb has captured galaxies caught in the middle of these transformations, revealing how environment shapes cosmic evolution. The cosmic web is not static. It's active, dynamic, constantly evolving. And yet, despite its overwhelming influence, dark matter remains one of physics' greatest mysteries. We still don't know what it's made of, whether it consists of unknown particles, exotic forms of matter, or something else entirely. Despite decades of effort, dark matter has never been directly detected in a laboratory. Experiments buried deep underground search for interactions between dark matter particles and ordinary matter. So far, nothing. Still, its presence is undeniable. Remove dark matter from the equations, and the universe we observe cannot exist. Galaxies wouldn't form, structure wouldn't emerge, the cosmos would remain a nearly uniform fog spreading outward into emptiness. Webb doesn't solve the dark matter mystery, but it reinforces dark matter's central role by revealing how quickly structure formed in the early universe. Webb shows that visible matter alone could never have done the job fast enough. Dark matter provided the head start. It built the invisible scaffolding, and everything we see filled in around it. This invisible framework explains why the universe looks the way it does today. The vast emptiness of voids, the dense richness of galaxy clusters, the filaments connecting them like cosmic bridges, all of it shaped by matter we cannot see. Yet this architecture operates inside a universe being pulled apart by dark energy. Dark matter builds structure, dark energy stretches space. The universe exists in constant tension between these two unseen forces. On smaller scales, gravity wins, allowing galaxies to form and clusters to grow. On larger scales, expansion prevails, pushing regions of space beyond every horizon, forever out of reach. Webb has shown us that the universe is not merely larger than expected. It's more organized, more interconnected, more dependent on invisible forces than we ever imagined. What we see, stars, galaxies, glowing clouds, is only the illuminated surface. Beneath it lies an unseen architecture, a cosmic skeleton built from matter we cannot touch, cannot detect directly, and cannot fully understand. And even this vast, interconnected universe is only what we can observe from our position in space and time. Beyond the cosmic horizon, the universe continues, shaped by the same invisible forces, unfolding in ways we can never witness. The James Webb Space Telescope hasn't just taken beautiful pictures, it's fundamentally reshaped our understanding of reality. We now know the early universe was far more active than expected, building galaxies, forming stars, and growing black holes at speeds that challenge our physics. We've discovered that the observable universe contains not hundreds of billions of galaxies, but potentially 2 trillion or more. We've learned that the universe is vastly larger than the light from its birth has had time to reach us, extending far beyond what we can ever observe. We've confirmed that dark energy dominates the cosmos, pulling space apart and hiding most of reality beyond an ever-expanding horizon. And we've seen how dark matter provides the invisible framework that holds everything together, shaping the cosmic web that defines the structure of existence itself. But perhaps the most profound realization is this: the observable universe, already incomprehensibly vast, may represent only a tiny fraction of what actually exists. Beyond the cosmic horizon, the universe continues. Galaxies form and evolve, stars ignite and die, black holes merge. Entire cosmic histories unfold, forever inaccessible to us, not because of technological limitations, but because the laws of physics themselves prevent their light from ever reaching Earth. We are observers trapped in a bubble defined by the speed of light and the expansion of space, and that bubble, while enormous is finite. Most of reality lies beyond it. This is both humbling and awe-inspiring. Humbling because it reveals how much we can never know. Awe-inspiring because what we can observe is already so staggeringly rich, complex, and beautiful. The universe doesn't need us to comprehend it. It exists on scales that dwarf human imagination. Yet here we are, tiny beings on a small planet orbiting an ordinary star in an unremarkable galaxy, using tools we built with our own hands to peer across billions of light years and uncover truths about existence itself. That might be the most remarkable fact of all. If this video opened your eyes to just how vast and strange reality truly is, please hit that like button. It genuinely helps the channel reach more people who are just as curious about the cosmos as you are. And don't forget to subscribe because we're diving into even more mind-bending discoveries soon. Thanks for watching, and remember, every time you look up at the night sky, you're not just seeing stars, you're seeing time, history, light that's been travelling for millions, sometimes billions of years, carrying stories from a universe far larger and stranger than we ever dared imagine. Until next time, keep looking up.